Hello and welcome to the Print Your Own Body workshop with me, Dominic Williams. I am a second year PhD student at the University of Manchester and I work in a field known as regenerative medicine. Now today I'm going to be introducing this term known as 3D bioprinting. Now some of you out there may have already heard of 3D printing, so consider bioprinting as the younger sibling of 3D printing. We're going to be doing an activity a bit later where you'll think about how to 3D print your own organ and how will you then communicate that to the end user, which will be a patient. So I hope you enjoy. But first, a little bit about myself. When I was at school, science was my favorite subject. I even ran a science club between year 9 and 13, where I was able to teach concepts of physics, chemistry, and biology to my peers, but also to younger years at the school. But when I left school, I had no idea what I wanted to study. I was really interested in medicine and veterinary, the surgical element, biology, but I was also really interested in the creative element of engineering, the designing, the manufacturing, and even the process. And so that led me to this subject known as material science and engineering. Now, materials are absolutely everywhere. And this only dawned on me whilst I was studying. From the car that your parents drive to and from work in, to the house that you live in, to the table you're working at, or even the pen and pencil that you're writing with right now, materials make up our life. But in particular, my interest focused on biomaterials and tissue engineering. So I was able to bring that passion for medicine and veterinary in with my intrigue of engineering. And then that led me into my PhD of regenerative medicine. So before we go any further, I'd like you to pair up. Now, in your pairs, I want you to think about this term biomaterial that I've mentioned. Now, consider it in the concept of medicine or your daily life, and you have 3 minutes in your pair to write down as many examples of a biomaterial in your daily life that you can think of. Go. Okay, great. So what is a biomaterial? Well, hopefully you've got some examples that you've written down from your daily lives. These could be a plaster when you fall over and you cut yourself, or if you cut yourself while you're cooking, you tend to put a plaster on things because it helps stop the blood from coming out and it also helps with the healing. Some of you may even know a relative or a friend who has had an implant, such as a knee replacement or a hip replacement, or even a valve replacement, as we have up here on the top right. But what is a biomaterial? Because I've asked you to come up with some examples, but I haven't actually explained it. Well, it is a natural or synthetic material, such as metal or plastic, that is suitable to be introduced into your body as part of a treatment. And effectively, what I'm saying is it's either natural or man-made. It replaces or supports a function that your body does, but importantly, it does not cause a negative response. Now, this negative response might be redness, soreness, or swelling. It might even be infection, or could even cause the breakdown of the material itself. Now, it's worthy noting that after surgery, you often have redness or soreness or swelling, which is actually part of the body's natural healing process. But if it's accompanied with infection or the breakdown of the material, then it often means that the biomaterial has failed. So an example will be a hip implant. Now, the white tissue that surrounds our joint in our hip is called cartilage. Now, because of injury or age or genetics, we can actually have a breakdown of this white tissue known as osteoarthritis, and it can be incredibly painful and it reduces the movement of the patient. Now, the engineering side of it is that we actually use a hip implant. Now, this implant has either a porous surface, so it's quite rough, and it has lots and lots of space for our cells to grow into. Now, when we put the implant into our thigh bone or our long bone in our leg, the bone actually merges with the metal implant, and that's known as osseointegration, osseo meaning bone. And this creates an incredibly strong bond between the material and our body. But we might also not want our implant to interact with our body. And so we can use a smooth surface implant, and we combine this with a polymer or plastic glue known as polymethyl methacrylate or PMMA. And this creates a barrier between our body and the implant. And so there's no interaction. So up close, we have our rough implant on the left-hand side, and that roughness is created by ball bearings. Now we heat these ball bearings between around 300 and 500 degrees Celsius, and it causes them to melt slightly and stick together. And this is known as sintering. It's a similar process to when we fire clay to harden it. Now, this creates a lot of space in our implant. And so you can see the yellow tissue here is actually bone, and that has actually grown into and around those ball bearings. But on the right-hand side, we have our smooth implant.
But I say smooth, but on a micro scale, so on the picture on the right-hand side, we can see there are lots of imperfections and scratches. And this has been specifically engineered so that the glue can attach to it. And so there is some bonding between the metal and the plastic, but remember, there's no interaction between the implant and the bone in that thigh area. But is there another way to treat osteoarthritis? Well, the answer is yes, and that is 3D bioprinting. So with 3D bioprinting, we can look at the natural structure of that white tissue, that cartilage, and we can then recreate it in 3D, and then we print it. But we also need to consider the mechanical properties of our tissue. And by this, I mean how strong it is, or how it needs to respond if it's compressed or stretched. Does it need to be stiff or soft? Bone is incredibly stiff, but our heart or our brain is very, very soft. Does the tissue need to support cells? So will it have cells inside it? Well, the answer is yes. How large does it need to be? Does it need to be about the size of a 2p coin, a bit like a heart valve? Or do we need to recreate an entire organ like a kidney? And the thing to remember here is that every cell in your body is about 1/100th of a millimeter away from a blood supply. And if it is any greater than that, then the cell struggles to live and the organ will die. So what is 3D printing? Well, for those that don't know, its scientific definition is it is a type of additive manufacture. But what does that mean? Well, we add layers one by one, and it is what we call a bottom-up approach. So we start at the bottom and we work our way up. And we do this by creating a stack of 2D objects. So imagine you were trying to create a cube, and I would say, right, you need to draw 1,000 squares on a bit of paper and then stack those up one after the other, and then you form your cube. With 3D printing, we can create incredibly complex designs and even customizable. So Formula One have employed 3D printing because it is relatively fast compared to the previous techniques. So if you were to cut material away or forge it by bashing it into shape, but it also means that we can create some complex geometry. So some complex designs, which would have been incredibly difficult to create unless by hand. And so we have our 2D square, and it is only one part of a 3D model. So compared to previous techniques, as I said, subtractive manufacture, where we have to cut away material. Imagine like if you're in the workshop and you're cutting wood away, that's subtractive, you're removing material. It's relatively fast and economic compared to these processes. We reduce the amount of waste that we produce because we only print the material that we need. We also have to create some support material. If I want to create it up here, I need to create a bit of support material, that a bit like scaffolding, which then supports whatever I'm printing. But then the ease of it is that we design it on a computer in 3D and then we print. So here we have a really simple design of a 3D printer. Now we have a display, which kind of means that we can load in our design. Remember, we've created it on a computer. We need to now tell the machine what to do. We have a filament reel. Now this is the source of our material. It needs to come from somewhere. We've got our extruder and a hot end, because in this case, we need to heat our material to melt it so we can print with it. And then a cooling fan, which actually helps cool the polymer back down. But how does this differ from bioprinting? Well, whereas before we use a solid filament reel, with bioprinting, we use gels, liquids, or soft solids. And these are generally made out of proteins. And so we can create complex structures, which copies what is in nature. Our body, our organs, our tissue holds itself together by a complex protein structure. And we recreate that using the gel, liquid, or soft solid. But we also need to control the environment when we're printing. It might be temperature, so very cold, around 4 degrees, or 37, which you'll know is our body temperature, or even the pH of the solution, how acidic is it? And these will impact how that gel or soft solid forms, and if it forms at all. But importantly, compared with previous printing, we can actually print with cells. We can add cells to our solution, and then when we put it at a temperature range or at a pH, at acidity, we can form our gel or soft solid with the cells actually inside. And so we can do this for that cartilage for osteoarthritis. And because of this, we are developing a way to 3D print organs, for example, heart. Now, this is actually an example which I've created for you. We have taken some cells and we've added them to our pink solution here. And then I have to mix this with a second solution, this blue solution here, in order to form the gel. So it actually stimulates the gel. And so here we are forming our droplets with our cells in them. And by dropping that into the second solution, it prompts it to form a gel. And so we form gel beads. And so now our cells are trapped inside these beads and we can monitor how they respond. So how will this help? Well, currently, some 5,000 people are waiting for an organ transplant in the UK at any one point. And we need an incredibly close match between the donor and the patient in order for that organ to be usable. And this can often mean that patients wait months or years for an organ. Imagine a liver or kidney transplant. But where can 3D printing help? Well, 3D bioprinting is the potential future for these treatments, or many of them. We can hopefully assist with the long waits of organ transplants, or even treat diseases such as osteoarthritis, which are incredibly common in our society. But it also offers us patient-specific care. So creating a perfect match for a patient, which is a perfect copy of what we already find in nature. So what's already in their body, we create. And we can also engineer the properties of whatever we create. It could be soft or strong, bone or heart or brain or nervous tissue or connective tissue. Depending on what properties are needed, we can look at potential engineering solutions. But we can also add cells, as I said. And so rather than it just being a hip implant that replaces the joint, we can create an active treatment, something that works with the body and hopefully degrades in a controlled manner to regenerate the area. So my task to you, you need to split into teams of 4, and you are a team of scientists who have cracked the key, the code to 3D printing organs. But you need to tell people about your discovery. You need to tell people about your eureka moment. So how are you going to do this? Well, I would like to design the packaging for your chosen organ. It should include a picture. This will be the wow factor. This will be the thing that people see. You should then detail some of the benefits that I've talked about regarding 3D bioprinting. Is it quick to produce? Is it patient specific? But then you need a name for your product. You need a name that is catchy and that people know. And so here is an example that I've done for you. And it's a 3D printed heart. But of course, I want a more imaginative, a more creative name than just 3D printed heart. I've detailed on the back a little bit about the process, but also some of the benefits. It's patient specific and it copies what's in nature. Here are some resources about some of the topics that I've talked about today. There's a bit on 3D printing at the University of Manchester, but then also more about the material science subject at the university too. Now, if you're interested in knowing more about be it bioprinting or the advancements in medicine or even the other aspects of science such as chemistry or physics in particular, then I would recommend that you check out The New Scientist and Jen just to pique your interest a little bit more and to help your understanding. But in the meantime, if you found something of interest to you, my advice to you would be to email the author or academic, and they will be pleased to answer any of your questions. So I hope you've enjoyed this workshop into 3D bioprinting, and hopefully you've learned something. Thank you.